Aluminium trifluoride is insoluble in anhydrous HF but dissolves on addition of NaF. Aluminium trifluoride precipitates out of the resulting solution when gaseous BF3 is bubbled through it. Give reasons. Now, let's take a look at this one by one. Good question actually. It says, first of all, it gives you data that aluminium trifluoride is insoluble in anhydrous HF. Fine. What does it mean? AlF3 solid, if you add. Now, please understand, many times, many substances are soluble or insoluble in water also. There are multiple reasons. AlF3 solid and HF. If you add them like this, apparently it looks like that there is no significant reaction, right? But dissolves on addition of NaF. This plus HF, no reaction, no dissolution also, nothing. But if you take AlF3, please note, when you're talking about anhydrous HF, that means HF is covalent, it is not dissociated. But in case you're having sodium fluoride, NaF, can you appreciate that this sodium fluoride, it has sodium ions and fluoride ions separate, obviously. There are cations and anions. And this F minus can always donate a lone pair of electrons to AlF3. Wow. Is that possible? Why not? And actually, you would get something very lovely. You will get AlF6 3 minus in solution. Okay, very interesting. This is a complex. Yes, Na3AlF6 you might have heard about. Cryolite is a very popular ore which was originally found in Greenland. It is used in it was used in metallurgy of aluminium. Nowadays it is artificially synthesized like this. So AlF3 would undergo a complexation reaction with NaF and it would form AlF6 3 minus. But for this, F minus has to donate a lone pair of electrons. If F minus has to donate a lone pair of electrons, F minus should possess a lone pair of electrons extra. Apparently, there were 3 lone pairs on HF, on fluorine in HF, but there was no negative charge. Since there was no significant negative charge, the tendency of donation of lone pair was not very high with HF or with fluorine in HF. The moment you convert this to NaF, Lewis basic strength, the tendency to donate lone pair increases. And because it donates, because it has negative charge, it says take electrons, take negative charge. It forms a complex. It dissolves. Lovely. Aluminium trifluoride precipitate out. Equilibrium shifts backwards. AlF3 precipitates out when gaseous BF3 is bubbled through it. That also is very lovely. Just imagine BF3 being exposed to this. Now, there are 2 Lewis acids, AlF3 and BF3, and F minus now has a choice. Why? F minus just has to donate lone pairs. Whomsoever is willing to take lone pairs, as a matter of fact, snatch lone pairs. It is much easier. And boron is much smaller in size than aluminium. They are in the same family. Boron is the younger brother, right? The smaller. And smaller and younger brothers say, more choosy. And whenever there is a choice, no, we want lone pair. Aluminium says, boron says, no, I want lone pair. What would aluminium do? Fine. Okay, boron, you're younger, you take the lone pair. So this is the way it happens. So you find that this donates a lone pair and BF3 accepts it. And it actually starts forming BF4 minus, which is much more stable than AlF6 3 minus. Because boron, being a smaller atom, has greater polarizing power. It's a stronger Lewis acid. So it takes away F minus. If it takes away F minus, the equilibrium shifts backwards as per Le Chatelier's principle. And as equilibrium shifts backwards, again you find along with AlF3 gets precipitated exactly in accordance with Le Chatelier's principle from chemical equilibrium. That, my dears, is the reason why F minus pushes it this side and adding BF3 pushes it back. Beautiful question. Take a look.